Okay, so yesterday we just did the introductory stuff and we talked about that count and the name and the two parts of a number. Today I want to get into how does this get into the calculations that we actually do every day. And the concept that ties it all together is another one of those relatively simple concepts that's undervalued and misunderstood. And that's the idea of place value. Just to review a little bit, we start at the end of the number. What's the place value of this last digit? The ones. Next is the tens and then hundreds. And those are actually our only three place values. That's what we call the base group. Those place values are repeated over and over again. Ones, tens, and hundreds. And ones, tens, and hundreds. The second set is called the thousands group. And then the millions group. And when we name a place value, we name its place value and its group. So this would be just the tens place. This is the 10,000s and the 10 millions and so on. And I'm not going to insult you by going through how we pronounce a number or anything like that. But there are some important things with these place values that I want to point out. First of all, knowing these place values helps us understand the structure of a number. Most of us are used to seeing a number written like that, 374. And most people don't realize that that is just an abbreviation. The full form of that number looks like this. 300s and 7 tens and 4 ones. And when it is written out like that, the structure of the number becomes way more apparent. You can actually see that every digit in the number is a count and a name. This isn't just a 7, it's 7 tens, and so on. So when we look at our basic operations, that structure is going to show us why we do the operations the way we do. The other thing that's very important from those place values is rounding. Let's say I ask you to round to the nearest 100, and I give you a number like 7,482. Well, what it's really asking us to do, round to the nearest 100, is actually referring to a number line. And what it's telling us is we consider a number line that's only numbered to the nearest 100. Like 7,300, 7,400, 7,500, pretend these are evenly spaced, 7,600, and so on. And then consider this number, 7,482, on that number line. Which 100 is it physically nearest to? 7,500. So that would round to 7,500, to the nearest 100. So when we say round to the nearest whatever place value, that's what it's really referring to, is on that number line, which one is it nearest to? Now, we don't want to have to draw out a number line every time we round. How were you taught to round to shorten this up? Well, first thing you have to do is find the hundreds digit. What digit in this number is in the hundreds place? The 4. So what that is telling us is that this is between 7,400 and then the next one up would be 7,500. So we know it's in that range. Then what did you do? Perfect. We look at that next digit in the next place, and that tells us which one we're closest to. If it's 1, 2, 3, or 4, we know it's closer to the one down below. It would be the 7,400. 6, 7, 8, or 9, of course, we know those are closer to the next one up, the 7,500. Now the 5 is right in the middle. You said 5 or above, we round up. Most of us were just told, well, if it's a 5, we just accept that we're going to round it up. But in reality, there's a good reason why we round it up. Let's say this is 7,452. Rounded to the nearest hundred still. The 4 is in the hundreds place. We look at that 5. Is this right in the middle, exactly halfway in between? No, why not? Yeah, because there's a 2 behind it. It's not 50, it's 52. So the reason when we see a 5 in that next place value, the reason that we always round up is generally there's stuff that comes after and it really is more than halfway there. The only time it really becomes an issue is if it's 7,450 exactly. Now it really is exactly halfway in between. The convention, though, is still that next digit is a 5, we round up, 7,500. In this class, that's how we will round. If you see a 5 in that next digit, whether there's anything after it or not, that 5 in the next digit tells you to round up. Now, you guys are in machining and CNC, so I'm going to show you something here. You don't have to write it down. You're not going to be tested on it, but I want to show this to you because you might run into it. In machining, we have to worry about error buildups, tolerance buildups. When I'm rounding numbers like this, just sketching out my number line quick for us. For every one, if I'm looking at that next digit after the digit I'm rounding to, this digit here, every time there's a 1 in that digit, it gets rounded down, we've lost a little information. But it doesn't matter, every time there's a 9 in that digit and we round up, we gain some information and that cancels each other out. For every 2 that gets rounded down, hopefully there's, on average, there's 8 that gets rounded up and they cancel each other out. For every 3 that rounds down, that's canceled out by the 7s that round up. Of course, the 4s rounding down, cancel out the 6s rounding up. You can see an issue here, though, with the 5s. What's there to cancel out the 5s? Nothing. So, in mechanical design, mechanical engineering, and in machining, and when it has to be extremely precise, they use a process, and this only applies to the 5s, called rounding to the evens. And what rounding to the evens does, let's say we're going to round to the nearest hundreds again. If I have a number like 3,750 or 3,250, I'm rounding to the nearest 100. So this is my hundredths digit, 7. I look and that next digit's a 5. Now again, if there's other information after it, we would just round it up. This only applies if we look at that digit, it's a 5, and everything else after it is all zeros. What we have to do then, rounding to, and again, for this class, we're always going to round it up. But rounding to even says if this is a 5 and it's all zeros after it, we look back at this digit in the hundreds place. Is that digit even? Is 7 even? No. So we're going to round that up to 3,800. So we rounded it to an even digit. Over here, the hundreds digit's the 2. We look at the next digit, it's a 5, and everything after it's a 0. So we look back at that digit in the hundreds place. Is it even? Yeah, so we leave it as 2, 3,200. Now, the even or oddness really has no significance. It's just the mechanism they chose to randomly pick whether you round up or down. Chances are half of the digits, half the time the digits will be even, half the time the digits will be odd. So all that is a way of making sure half the time we round it up, half the time we round it down, so that it cancels itself out in this little chart of errors here. Half the fives get rounded up, half of the fives get rounded up, half of them get rounded down, so they cancel out. Now, again, I'm not going to ask you to do it in here, but you may run into calculations and stuff on a blueprint from a mechanical designer or a mechanical engineer. And you might see that it looks like they rounded it down. They rounded it wrong because it's 0.5 or whatever they rounded down. And that's what they're doing, is they're evening out their round off errors. And later in the class, we talk about tolerances and allowances. I'm going to look at that as well. How if you work at the upper end of all your tolerances, you can have that. It's called the tolerance buildup or tolerance compounding that throws things off too. Okay. So enough of that. Since I threw out number lines, by the way, you guys probably remember these old problems like this. Fill in the symbol between the numbers. So that would be less than, or whatever. A lot of people have a hard time remembering, what the less than symbol is. You're probably taught, treat that as an alligator, and the alligator wants to eat the bigger number. Which, unfortunately, that's still the best analogy I can come up with. Probably politically incorrect. Somebody told me that it's the bully, and the bully points at the little kid and laughs. Probably not the most politically correct one to use in this day and age. This is actually referring to a number line. If you have 3 and 8 on a number line, this is asking what side is the 3 on? Well, here's the 8. The 3 is on that side. That's where that symbol comes from. The arrowhead on that end of the number line. Okay. Enough side notes. Let's get back to the material here. So now let's look at, and we're going to kind of buzz through this really quickly. And I'll explain why as we go. Let's look at the operation of addition with our whole numbers. Let's take something like 347 plus 251. As we mentioned, 347 is really 300s and 4 10s and 7 1s. 251 is really 200s and 5 10s and 1 1. If you recall from yesterday, when we talked about adding and subtracting, there were 2 things. One, to add or subtract, you must have the same name. Fractions, that's common denominator. Decimals, you line up the decimal point. Inches, add with inches, other units and stuff like that. The second thing, we always combine the counts, but when we add or subtract, we keep the same name. So what that means for our addition over here, when you learn to add, it was always stressed to you, make sure you write your numbers neatly and line up the columns, right? Well, the reason for that is this right here. When we add or subtract, we can only combine things that have the same name. Remember this here, each digit is a count and a name. This isn't just a 4, it's 4 10s. That 4 10s can only be combined with other 10s when we add or subtract. So lining up the columns is making sure we're combining digits with the same name. So let's go ahead and do that. We're going to go right down the columns here. We can only combine hundreds with other hundreds. So 3 and 2 make 5. We keep the same name, so that's still hundreds. 4 and 5 makes 9. Again, that stays tens. 7 and 1 makes 8, and that's still ones. So 598 is our answer. Now, as I was doing that, some of you may have picked up that I did something a little strange there. Can you tell me what it was? I went left to right. We're used to doing our addition and subtraction and most of our other operations right to left. For addition, why do we usually go right to left? In case you got to carry. So we might have 384 plus 497. We would typically start on the right and work our way back to the left because we might have 4 plus 7 is 11. We keep the 1 and we carry the 1. 1 and 8, 9 plus 9, 18. So we keep the 8 and carry the 1. 1 and 3, 4 plus 4, 8. So we had 881. Now, believe it or not, that process there of carrying is a relatively new process. By relatively new, I mean like a couple hundred years old. Before carrying was popular, there were a lot of other ways that numbers could be added. One of them looked like this. 3 plus 4 is 7. 8 plus 9 is 17, so 7 drop the 1. 4 and 7 is 11, so 1 drop the 1. 7 and 1 is 8. 7 and 1 is 8, and 1. Get the same answer. Maybe a little bit longer, but it gets there. Not trying to change the way you add numbers. I'm showing you that for the main reason is we've always been told that there's only one correct way to do things in math. It's absolutely not true. I could show you 4 or 5 different ways to add numbers that would always give you the correct answer. It would always work out. There are several different ways. So just because the way you're doing something is different than the way I've showed you doesn't mean it's wrong. It may still very well be a legitimate way of doing it. If you're not sure, come and talk to me. I'd be happy to look at it and let you know if it's something that's going to work every time. I think I'm going to get on my soapbox for just half a minute here. Right, one of the biggest mistakes that gets made with teaching math, one of the most common reasons why a lot of people struggle with math and don't necessarily like math is because we tend to teach just one way. And you have to do it this way because that's the way I showed you. But everybody's mind works different. Everybody's mind is wired to do math, but everybody's mind is wired differently. And trying to teach everybody the same way, well, people whose minds work that way, it clicks and it's just fine. People whose minds work a little bit differently, that's not the way they need to see it done, so they don't understand it and they get frustrated. So I think that's probably the biggest mistake that is made in teaching math, is trying to force everybody to do it the same way. So like I said, if you have a way that's slightly different than the way I do it, talk to me and we'll work through it and make sure it works every time. Because if that's the way your mind works, that's going to work better for you. You're going to understand it better, and it's going to be less frustrating for you. My goal here isn't to turn you into me. It's to give you what you need to be successful in your job and stuff like that. Okay, I'm off my soapbox now. Back to the regular math. I also fully acknowledge you guys have calculators, and you're probably going to use them. And something like this with 3 digits, you're probably not going to whip out the paper and pencil and start doing it by hand. Many of you are probably going to punch it in. But before you punch it in the calculator, I would ask you to look at 384, and so that's close to 400. 497 is close to 500. 4 and 5 is 9. Hundreds and hundreds stays hundreds is 900. I'm expecting that answer to come out close to 900. The reason I say that is it happens to me all the time. I've got these fat sausage-like fingers. It's not uncommon for me to take something like 384 plus 497, and the calculator spits out 5,271. If I'm not paying attention, I write that answer down, I go on the left because the calculator's always right. Well, what happened? Yeah, I accidentally hit an extra key in there. And it's also not uncommon for me to have 384 plus 497 is telling me it's 531. What happened there? Yeah, one of the keys didn't register when I was typing in the 384. Happens a lot. If you're not paying attention, it happens. If you have this little bit of an estimate here, it catches that mistake. It stops it. Wait a second, that doesn't sound right. Let's try again. It doesn't stop every mistake, but it stops a lot of the really bad ones. When I worked engineering before I came here. When I did engineering work, I saw it happen all the time. Somebody would punch something into a calculator and they get that answer, write it down, and they keep working with it. Well, they'd have an hour and a half worth of work that was useless because it was based on one calculation that was wrong. Yes, sir. Yeah. Always double check it. If nothing else, work it backwards and see if you get back to where you started. Let's look at subtraction quick. Let's take something like 874 minus 253. Now, I'm not going to write this out in its long form because I think you guys get the picture. When we add or subtract, you line up the columns because you can only combine digits with the same place value. So once it's lined up, we just go ahead and subtract. 8 minus 2 is 6, 7 minus 5, 2, and 4 minus 3, 1. 621. What did I do there again that's a little bit off? I did left to right. We usually, when we subtract, go right to left in case we have to not carry, but there we go. Borrow for subtraction. We might have like 737 minus 298. So we start on the right and work our way back to the left because 7 minus 8 doesn't work. What do we have to do? Borrow from the 3. It becomes 2. This becomes 17. 17 minus 8 is 9. 2 minus 9? Can't do it. Borrow from the 7. That's a 6. And this is now 12. 12 minus 9? 3. 6 minus 2? 4. So 439. Just like with addition, borrowing is a relatively new process. So an alternative way of doing this, 7 minus 2 is 5. 3 minus 9 can't be done, so we're going to take from the 5. That's going to be a 4. This is a 13. 13 minus 9 is 4. 7 minus 8 can't be done, so we take from the 4. That's now a 3. This is 17. 17 minus 8 is 9. Put the same answer. Again, I'm not trying to change the way you subtract. I just want you to see that there are multiple ways of doing it. Realistically, again, if I'm punching this in the calculator, that's about 700. This is about 300. 7 minus 3 is 4. Keep the same name of hundreds. I'm expecting an answer around 400. My calculator spits out 439. That's reasonable to me. I know it's not horribly far off. Well, let's look at multiplication. When we multiply, when you first started learning how to multiply in about first grade, we had something like 5 times 3. Before you memorized your multiplication tables, and before you just knew that that had to be 15, how did you figure it out? Yeah, repeated addition. 5, count on your fingers. Yeah. 5 plus 5 plus 5. We took 3 5s and added them together. Gave us 15. Multiplication is repeated addition. If I look at a long multiplication, like 32 times 21. I am going to write these out in long form. 3 10s and 2 1s. 2 tens, and 1 1. When we multiply, do we need the same name? No. When we multiply or divide, we do not need the same name. And again, as always, we're going to combine the counts, but for multiplication and division, we also combine the names. Which is what you were saying. I didn't mean to cut you off. So we don't need the same name when we multiply. So what that means is the 3 tens here can not only be combined with the 2 tens, but it can also be combined with the 1 1. In fact, every digit in one number can be combined with every digit in the other number. And long multiplication is just a process of organizing it to make sure that every digit in the first number gets combined with every digit in the second number. Now, I just showed you up above multiple different ways of adding and subtracting. There are multiple ways of doing the long multiplication. In fact, depending on what region of the country you're raised in, or if you were taught in a different country, where you start and how you organize it is different, but it's the same basic idea. In this area, most of us were taught that you start with the bottom number and the last digit. That would be the 1 1 here. Then you start combining that with the digits of the top number, and we work right to left, backwards, just like we did with everything else. So you combine it with the 2 1s. So we'll multiply. We combine the counts. What's 1 times 2? 2. But we also combine the names. 1s times 1s is 1s. Then we move over to the next digit of the top number. Combining the counts. What's 1 times 3? 3. Combining the names. 1s times 10s is 10s. Now, what have we been taught that we have to do down here then before we move over to that next digit? Put a 0 here. Or some of us were taught to just leave a space there, depending on where you learned. Now that we have that in there, we move over to this next digit. And the reason for that 0 is going to become apparent now. So now we've got 2 tens times 2 1s. What's 2 times 2? 4. But we still have to multiply the names. 10s times 1s is 10s. We needed that 0 here so that our place values stayed lined up. Now we have 2 tens times 3 tens. What's 2 times 3? 6 tens times 10s is hundreds. And now we just combine our digits. We add our columns. We got 2 1s and 0 is just 2 1s. 3 tens and 4 tens, 7 tens, and then 6 hundreds. So 672. So you can see the process of long multiplication comes from what I showed you yesterday with the count and the name. Now again, I'm pragmatist. I realize that a lot of you, when it comes to long multiplication, are going to punch in the calculator. So again, I would hope you'd look at this and say that's about 30. This is about 20. 3 times 2 is 6. But now we're multiplying, so we combine the names. 10s times 10s is hundreds. What's the shortcut for combining the names? Does anybody know? Combine the zeros. There you go. If I have 4,000 times 200, I'm going to take 4 times 2 is 8, and then I have 1, 2, 3, 4, 5 total zeros. I put 5 total zeros on my. Division. In every form of number, division is the one process that has been mutilated. I mean, it's been abbreviated and shortened and changed to try to make it easier, to the point where it's a mechanical process that has absolutely nothing to do with the process of division. So what I'm going to do here is I'm going to show you the actual long process of division, and then I'm going to show you what you were most likely taught, so you can see where one comes from the other. So this first piece I'm going to do here, you don't need to write down. So division, we said multiplication was repeated addition. And I told you yesterday that multiplication and division follow the same rules. Just one's going forward and one's in reverse. So if I have something like 24 divided by 8, we said that multiplication is repeated addition. Does that mean I can treat division as repeated subtraction? Yeah, 24 minus 8 is 16. 16 minus 8 is 8. 8 minus 8 is 0. I was able to subtract the 8 from 24 1, 2, 3 times. 24 divided by 8 is 3, because I can subtract 8 from 24 3 times. In fact, this is where our remainder system comes from. 30 divided by 7. 30 minus 7 is 23. 23 minus 7, 16, right? 16 minus 7, 9. 9 minus 7, 2, and we can't subtract 7 anymore. So 30 divided by 7 is 1, 2, 3, 4, with a remainder of 2. Because we can subtract the 7 4 times and there will be 2 left over. Now, as we go through the semester, we'll see different ways of expressing that remainder. When we do fractions, we probably express it as 4 2/7. As decimals, it might be 4.285711429, and so on. For right now, we'll leave it as just remainder of 2. Well, let's step it up just a little bit in our level of difficulty. Let's say that we have, let's do 72 divided by 3. It would not be practical to start subtracting 3 from 72. But what I can do is I can subtract it in big bundles. 10 times 3 is 30. If I subtract that, that's 42, right? I've just subtracted my 10 3 times. If I subtract another 30, I'm left with 12. Well, that's another 10, so I'm now at 20 times that I've subtracted the 3. Can't subtract 30 anymore, so I'm just going to subtract 3 individually. 12 minus 3 is 9, that's 21 times. 9 minus 3 is 6, that's 22. 6 minus 3 is 3, that's 23. Subtract 3 once more, I'd be at 0. So 72 divided by 3 is 24, because let's subtract the 3 24 times. But notice I didn't have to do it individually. I could do it in bundles. I could do it in groups of 10 or 100 or so on. Long division is nothing more than a process of organizing this so that we can divide and subtract in big bundles like that. Let me show you what I mean. Oh, let's say that we have 6,900 or 69,824 divided by 21. Again, I am not about to start subtracting 21 from 69,000. We really don't have that kind of free time. But I can look at it in large bundles. Well, how do I know how large of a bundle to try? I look at the place values of the number I'm dividing in the 69,000. The first digit here has what place value? So the 10,000s place. So what's 10,000 times 21? Careful. 210,000. Can I subtract that? No, that's too big. So I go to the next place value, which would be 1,000. 1,000 times 21 is 21,000. Can I subtract that? Yes, I can. In fact, I can subtract it more than once. I'm going to shorten it up a little bit here. How many times? I could subtract it actually 3 times. 21,000 times 3 would be 63,000. So I'm going to subtract that. I'm left with 4, 2, 8, and 6. What I just did there was I subtracted the 21 in a bundle of 1,000, but I did it 3 times. So 1,000 times 3 is 3,000. I just subtracted the 21 3,000 times. A lot quicker than doing it individually, right? Hopefully. Next place value is 100. 100 times 21 is 2,100, 2,100. Can I subtract that from what's left? 3 times again. 2,100 times 3 is 6,300. So that'd be 4, 2, and 5. So again, I subtracted a bundle of 100 and I did it 3 times. So I just subtracted the 21 how many more times? 300 times. 100 times 3 is 300. My next place value is 10. 10 times 21, 210. Can I subtract that? Yes, I can do it twice. 210 times 2 is 420. Leaves me with 401, 104. Again, I just subtracted a bundle of 10 twice, so I subtracted it 20 times. Last place value left is just the ones. 21 times 1 is 21. And I can subtract that not quite 5 times. So I have to stick with 4 times. That would be 84. There's 20 left over. So I just subtracted it 4 more times, the remainder of 20. So when I divide 69,824 by 21, I get 3,324 with that remainder of 20. Now you might be looking at that thinking, that looks nothing like what I was taught for long division. It's actually exactly what you were taught. It just looks very different because you were taught a very extreme abbreviation of this. What we were taught to do, does 21 go into 6? No, so we leave it blank up above the 6. That's exactly what we did here. We tried the 10,000, it was too big, so we moved on. Does 21 go into, we go to the next digit, 69. Does 21 go into 69? Yeah, how many times? 3. 3 times 21? 63, we subtract to get 6. What we just did there is exactly what we did here. We just left all the zeros off. Now, depending on where you were taught, most of us were taught to just bring down the next digit. Some people were taught to bring down the rest of the number. And it doesn't matter. They're pretty much the same process. It just looks just slightly different. Does that 21 now go into the 63 or 68? Yeah, 3 times. Put 3 there. 3 times 21 is 63. There's 5 left over. Once again, this looks exactly like this, only we left all the zeros off. Notice we got the 5 left over, 5 left over. Bring down the 2 and keep going. So this really is the process along division over here. It's just what we were taught. We took out a bunch of the steps and shortened it up. And the problem I have with that, back on my soapbox for half a minute again, is now it just becomes a process you have to memorize how to do it. It doesn't make any sense. This repeated subtraction probably confused the heck out of you guys because you haven't seen it before. But if you did it a couple of times, it actually makes sense. You can see the reason why you do each step in it. When you abbreviate it like this, like I said, now it's just a process. You've memorized how to do it, and hopefully you remember it because there's really no good reason why you do each step. And that's the one thing, like I mentioned yesterday, I'm hoping that we can correct for you a little bit throughout this first semester at least, is some of those things that you were just told do it and memorize how to do it. Hopefully we can show you why so you can figure out a little, understand a little bit better how you're doing things and why you're doing some of the things you do. The reason for that is, again, as I mentioned, a lot of what we do in this class is going to be word problems and solving word problems. If you don't understand why you do things a certain way, when you come to a new problem, it's going to be really tough to figure out how do you do that new problem because you don't understand. You just memorized a process for solving the other ones. With that said, depending on what clock you believe, I'm going to believe the clock on the computer. It's 8:13. We have about 7 minutes left. So I'm going to give you that 7 minutes to start working on your homework. The way I handle it, since you guys have 2 textbooks, I'll refer to it as just the big book and the little book. Today we're going to work out of the little book. And it's divided up into units. Units 1, 2, 3, and 4. That's just addition, subtraction, multiplication, and division. A lot of word problems. Yeah, I know you're going to get used to them. Unfortunately, life is a word problem. Unless I say otherwise on assignments, when I give an assignment like this, I am always referring to just the odd numbered problems, the 1, 3, 5, 7. In both of your books, the answers to at least the odds should be in the back of the book. So as you're doing your homework, you can go back and check your answer to make sure you're doing it right. I do this for a couple of reasons. One, I don't collect your homework and grade it, so I want you to know that you're doing it right. Two, rather than doing 20 problems and then grading it and finding out you did them all wrong and now you've developed a bad habit, I'd rather have you do 1 or 2 problems, check your answer, make sure you're doing it right before you keep moving on. Doing something wrong is actually worse than not doing it at all because it develops a bad habit. And now you've got to unlearn what you're doing wrong and before you can learn how to do it right. So make sure you're checking your answers as you go. And like I mentioned yesterday, as you're doing homework, if you do the first couple and they seem extremely easy, feel free to skip ahead a few problems, do some of the more difficult ones. In these chapters, make sure you're doing, some of the later ones in the sections as well, because those are the more difficult ones. If you hit a problem that you look at, it just makes no sense, a lot of these problems will build on the previous question in the unit. So sometimes you may have to look back at the question that comes right before it to see, it might define a formula or define something that you have to use in the next like 3 or 4 problems. So make sure you're checking on that. But it's all part of being able to search out answers and find the information you need. Okay, I will give you guys the last 5 minutes or so to get started on your homework. At 8:20, we'll end class. 1, 2, 3, and 4. I usually won't warn you, but tomorrow might be your first quiz. 1, 2, 3, and 4. Yeah, you may have to just pair up with people for now and look on and work on stuff.